Passage planning is a key element of bridge resource management, forming the foundation the bridge team will use to ensure the vessel's safe transit along its intended route. A passage plan is a comprehensive, berth-to-berth guide, developed and used by a vessel's bridge team to determine the most favorable route, to identify potential problems or hazards along the route, and to adopt bridge management practices to ensure the vessel's safe passage. During passage planning, portions of a voyage that have the potential to pose the greatest risk should receive additional review, and the limits and conditions for undertaking those portions of the voyage set in advance. Having made a full appraisal using all information at hand pertaining to the passage, the officer of the watch, under the authority of the master, is to prepare a detailed plan for the passage. In this stage, the intended courses of the ships are actually laid out on the charts of suitable scale, and all additional information is marked. The plan is laid out from pier to pier, including the pilotage waters. The adage that the shortest distance between 2 points is a straight line is also true in nautical navigation. Passage planning includes looking for hazards and avoiding them. It is a good practice to mark dangerous areas such as nearby wrecks, shallow water, reefs, small islands, emergency anchorage positions, and any other information that might aid or endanger safe navigation. The person planning the passage decides on the margin of safety around hazards and also the most economical route. ECDIS has an automatic check function that should be used throughout planning stages. The effectiveness of the automatic check system relies on the accuracy of the safety parameters set by the user. A passage plan is prepared with a minimum under keel clearance in mind. Most of the time, that UKC is set by the owner of the vessel. The passage plan must be prepared with economy in mind, so tide height and current information is required. The navigator must also be skilled in the use of the echo sounder on board. ECDIS has by default a depth alarm system which sets the required depths for navigation. Different contours and depths indicate different parts of navigational waters. The following are some of the most common issues regarding navigational waters. Shallow contour indicates the depth below a vessel could run aground and it is equal to vessel's maximum static draft. Safety depth equals maximum static draft plus UKC, as per company's policy, plus maximum squad less height of tide. Safety contour is calculated same as per safety depth and activates an alarm when depth is less than the setting. Deep contour indicates the limit of sea area where shallow water effects occur that can affect a vessel. It should be estimated twice or 4 times the draft of vessel, depending on the depth of water available. The courses plotted on the chart are the intended tracks of the vessel through the voyage. These tracks should be the safest, economical route. The conditions from current predictions, navigational warnings and weather forecasts, as well as expected traffic could be not present and the master could decide to deviate from the plan. Passage planning requires the identification of no-go areas on the chart. In some parts of the voyage, the navigator will find clearing lines and bearings helpful. These should be considered and stated on the chart for all watchkeepers. The passage plan should also highlight leading lines and natural transits wherever they will be helpful. Parallel indexing is a technique used as a measure to monitor the progress of a vessel on the track and to minimize the cross-track distance and to keep vessel at a safe distance from the navigational hazards. Parallel indexing is a method where the distance between the intended track and a good, stationary radar target is measured. A line is then created on the radar display, the same distance from the origin or ship's position. This line is in the same direction as the intended track. As the vessel progresses on the leg of the voyage, the position of the echo of the good radar target is compared with the line created. Parallel indexing does not remove the requirement for position fixing. Parallel indexing is a technique used as a measure to monitor the progress of a vessel on the track and to minimize the cross-track distance and to keep vessel at a safe distance from the navigational hazards. Parallel indexing is a method where the distance between the intended track and a good, stationary radar target is measured. A line is then created on the radar display, the same distance from the origin or ship's position. This line is in the same direction as the intended track. As the vessel progresses on the leg of the voyage, The position of the echo of the good radar target is compared with the line created. Parallel indexing does not remove the requirement for position fixing. Many navigators now make use of computer software to generate an optimus track. The result is that their vessels are all heading for the same waypoints on similar, or reciprocal tracks. Inevitably, this can lead to dangerous close encounters. There is a common rule in aviation to leave all recognized waypoints to port. Depending on the amount of sea room available, this might be a few cables, and in open water a mile or two from the waypoint. This offset from an optimus track for all vessels heading towards the same waypoint would allow more room for maneuver, and almost all near misses created by common waypoint navigation could be avoided. Galera Point is an area where this might occur. Waypoint selection should be triple-checked. The courses generated should be triple-checked for hazards. The correct input of waypoints into the database should be triple-checked. The passage plan should also include information about notifying the engine room and about adjusting speed for a particular estimated time of arrival. Passage planning on an ECDIS requires almost the same procedures as for a paper chart, and the navigator must follow the same best practice guidelines as per the Bridge Procedures Guide. However, with ECDIS, the process is complicated by the fact that the navigator needs to know what information is already incorporated into the ECDIS and what is not, and this is where a weakness of ECDIS is exposed. The users must do their own appraisal for comparison with ECDIS. When approaching constrained waters, the vessel might be in a position beyond which there is no possible action but to proceed. For example, the vessel enters an area so narrow that there is no room to return. It is for this purpose that a position is drawn on the chart showing the last point wherein the passage can be aborted. The bridge team must always be aware that the events might not go as planned and that emergency action might be required. Contingency plans account for such situations, clearly shown on the chart so that the UO can take swift action in such a jam. Contingency planning will include alternative routes, safe anchorages, waiting areas, emergency berths. Once the navigator has all the relevant documentation in hand, the plan can commence, and the first thing to check is whether waypoints for that passage already exist in the ECDIS database. If so, it can be uploaded for use and, by running an initial check, the ECDIS will verify if the plan is safe for the dynamic parameters previously set. The main problem that traditional mariners find with this is the small screen size, which makes it difficult to obtain outline overview obtained from a small-scale paper chart. However, in practice, the advantage of ECDIS is that by putting in departure and arrival points, any obstructions will be identified and the navigator can then move waypoints and recheck the outline route.